And similarly, it was a probability of 2 heads in 2 tosses. Alright, probability head on the first and head on the second, and that's a half times a half again, or a quarter. But what if I say, what's the probability of 1 head in 2 tosses? Okay, now you can't tell me that there is one sequence there. What we have here, this is either probability of head on the first, tail on the second, or the probability of tail on the first, head on the second. And notice when I said this, I said or, and I can do that because I cannot, both these events cannot occur at the same time. That's what they're called, mutually exclusive. It's a concept I'll talk about a little bit later. So I have this 1 head in 2 tosses is sort of like a compound event. Okay, there's no overlap in these two, so I can just multiply the two. So it's a half times a half on the first, and then a half times a half on the second. Right, a quarter plus a quarter is a half. So when the order is not specified, as it was in this specified in this particular example, all right, 1 head in 2 tosses, that did not say I want the head first, then the tail, or vice versa. When the order is not specified, all right, the probability of such an event, we do as follows: the number of ways in which we can get, say, 1 head in 2 tosses, there are 2 ways, times the probability of 1 way. And I'll take a few different examples. Alright, probability of 1 way is a quarter. And so we have the answer a half again. It'll take a while for you to understand that the probability of each of these ways is the same. It doesn't matter if the head's first or the tail second, or the head. No, sorry, the head is first and the tail is first. The probability of getting 1 head and 1 tail, regardless of the order, is always the same. Okay. So, coin tossed 3 times. So what's the probability of a head on the first, head of the second, and a head on the third? Again, it's a half times a half times a half. The probability doesn't change, and it's 1/8. Or let's say probability of a head on the first, tail on the second, tail on the third. Alright, probability of a head is a half, tail is a half, tail on the third is a half, and again, 1/8. So probability of 0 heads. Okay, 0 heads means there's only one way of doing that, right? Tail, tail, tail. Again, half times a half times a half. It's 1/8. But again, remember, this is one way of doing this times the probability of that one way. Okay? Probability of 1 head in 3 tosses. Well, off on the side you can say, well, how do I do that? Well, I can get a head, tail, tail, I can get tail, head, tail, or I can get tail, tail, head. Alright, so there are 3 ways. Alright, so number of ways, 3 ways times the probability of 1 way, just pick one, head, tail, tail, and as we've seen before, that's going to be 3 times 1/8 or 3/8. Probability 2 heads, again in 3 tosses. Well, again, somewhere you try to figure out the number of ways. Head, head, tail, head, tail, head, tail, head, head. Don't worry, we're not going to do this for 20 tosses. There are other ways of doing that, which we'll see in the next module. But there are 3 ways again, times the probability of 1 way. Head, head, tail. Again, 3 times 1/8 is 3/8. Probability of 3 heads. Right, it's like actually the probability of 3 tails. Right, there's 1 way times the probability of that 1 way. Head, head, head. And again, we get 1 times the probability of that is 1/8. Okay. Notice that what we have is what we'll see later is a probability distribution. It's a good concept to see now. Alright, so X number of heads on 3 tosses of the coin. So we could either have no heads, 1 head, 2, or 3 heads. And from the previous screen, you see the probability of no heads was 1/8, 1 head, 3/8, 2 heads, 3/8, 3 heads, 1/8 again. And all these probabilities add up to 1. Okay? So, basic rules of probability apply here in different sequences, but we have all the probabilities adding up to 1, right? And we have each of these probabilities somewhere between 0 and 1, and we can work them out by basic counting rules, etc. Alright, going to write up an example here. What I want you to do is to try this, pause the video and then try it, and then watch my answers later. Let's say that the probability of rain on any day during the summer is 30%, and that probability is independent define that concept better later on of rain on any other day. Independence in this scenario will be equivalent to sampling with replacement in a very crude sort of way. Okay? That is, just like a coin toss, the probability of getting rain tomorrow is independent of getting rain today, just like the probability of getting a head on the second toss is independent of getting a head on the first toss. Okay? That of course may not be true, but we're going to assume this is true, and especially true during the summer. Let's say that we have a 3-day event. that's outside, and we're looking at probabilities. That event could be golf, sailing, camping, whatever, and we'd like it to not rain. So, would you to determine the probabilities. Probability of no rain on any day. Probability of rain on all three. Probability of rain on the first day, no rain on the second, and no rain on third. So probability of rain on exactly one of the 3 days. And lastly, the say the probability of rain on at least one of the 3 days. Okay. To make this exercise work to your benefit, pause the video right now, and when you're finished working on the problem, either you can't work any further or you're done, continue the video and I'll see the answers.